Okay, so now we're in lecture 24, and so um, next weekend, and I guess we'll determine a date, but it'll probably be on a Saturday. I'm sorry, a Sunday, and we'll pick a time of the practice exam, and then the following week on Friday we'll actually have the exam. Okay, so for review, um, yeah, so. Um, One thing I want to mention, I made a mistake with the DC blocker. And the issue is that I, I had an equation here that led you to believe that the DC voltage was being blocked, but it's not the voltage, it's the current, the DC current is being blocked. And of course, if you think about it, it makes sense that it would be the current, not the voltage. So what happens is that the capacitor becomes fully charged. After it's fully charged due to the DC voltage, then no more current is able to pass through. So you do have an AC signal of current that passes through, but not the DC. That's why. So the DC blocker corresponds to the current and not the voltage. Okay. And I have a couple of slides that go into more detail about that. So I corrected a lecture 22, and this is like the summary of that part. And I posted it online. Okay, so anyway, so this is the blocker or coupling capacitor, the bypass capacitor right here. We also did analysis with the quiescent point for DC and AC analysis. We looked at the diode and also looked at the gain of the diode, which is just a slope at that point. I'm sorry, not the gain, the conductance, sorry, of that point right there. Okay, and for review of last lecture, we looked at transconductance and the difference between that and transresistance. We also looked at a two-port representation of an NPN transistor, and we looked at the hybrid pi model, which is the most common model that you'll see in papers. We also looked at the early voltage right here. Okay, so it's the voltage that these all project to. Like if they were straight lines, it didn't curve down right here. If they kept on going, they would project to this voltage right there. And we looked at the transconductance right here for the transistor. And as you can see, it looks a whole lot like the diode, at least in this region right here. After that region over here, no. But in this region, it looks almost like the diode. Okay, but it's for the transistor. And we also looked at intrinsic voltage. Okay, so so more on this DC blocker, which is also the same thing as an AC bypass, but it's with respect to current. Okay, so think of it like this: you could have this current signal coming down, and this current signal is a combination of DC, as a DC component, and it has an AC component. So you could think of it as the DC component going around this direction, and the AC component going in this direction. And one way to look at that is, well, the current likes the path of least resistance. And for DC, since this can become fully charged right here, depending on what the voltage is, then once it's fully charged, DC can no longer go this direction. So this would then have the largest resistance to that DC current. So then DC would go this direction. But that's only after it's fully charged. Okay? So it says here that capacitors block DC current signals once the capacitor is fully charged. This could be used to make a much cleaner DC current signal. Okay? And here's an example. So for example, if you want to block the 50 to 60 hertz ripple that's found in like all these outlets right here. Yeah, so there's this ripple found in these AC in these outlets. So what you do is you choose your capacitor such that the reactance value X of at most 10% of the resistor's value. So for example, whatever this resistor value is, a good rule of thumb is if you make the reactance here 10% of that, then most of the current, well, the DC component will go this direction, and you'll get rid of that AC component. And here's the example. So let's say you have a resistor of 500 ohms, and then what you do, you determine your capacitor with that in mind as follows. So here's the reactance, 1 over omega C, and omega is 2 pi f, frequency in hertz, okay? And you want this reactance to be less than 10% of the resistance right here. You can make it smaller if you want, but 10% is usually a good value. So if you just solve this equation for capacitance C right here, you'll see that the capacitance value needs to be greater than 1 over 2 pi f 10% R. And if you plug in the values of R being 500 ohms, frequency of 60 hertz, you'll get this value right here. So that means your capacitor, if that has 66 microfarads, then now do the job. Okay, then you have like a pretty clean DC signal coming through here. Okay, so here's a common thing that's done. So, and you can also think of it as a bypass too, AC bypass. So the AC portion goes through here quite easily and not in this direction. So in terms of AC, this is sort of like a, so it's a whole lot easier. Like this path right here is the path of least resistance for the AC if you want to think about it that way. So it's kind of like, it's sort of the opposite between AC and DC, between the resistors and capacitors. Okay. All right, and now if you did want a voltage, what you could just use is a transimpedance amplifier, right? So instead of these going directly to the ground here and here, then you could think of this as a virtual ground, and the virtual ground is connected to the transimpedance amplifier. So that's grounded, and that's copied right here, so then this is grounded. Same here. This is grounded right here, so the transimpedance amplifier input right here is grounded. So, but once the current goes through here, this AC signal that's going back and forth like that, so it's going to go through back and forth through this feedback resistor, and if that's grounded, if that's 0 volts, then if it's going this direction, then this voltage is going to be right here. So you have your voltage, but it's your AC voltage, and it's proportional to this current right here. So if the current is going this direction, then the voltage is less than 0 volts. But it's sinusoidal, so once your current starts going this direction, then this voltage over here is higher than that 0. In this case right here, you have your DC current just going through right here, passing through. That's going to be 0 volts, and it's going through. It's going to lose voltage, a drop in voltage when it goes down here. So this is going to be less than 0 volts right here. And it'll go either into the nose of the amplifier or go out if it's connected to something. Okay. Yeah, so the TIA is used to convert current to voltage. That's common use for that. Okay, so any questions about my screw up on the blocking DC? Okay, hope that clears it up. Okay, so I forgot to write more stuff. That's not the only thing. So we have more things. I just forgot to type it. Okay, so let's start with equivalent circuit models. Okay, so this is sort of like continuing where we left off last time. Okay, so depending on the type of analysis, it may be easier to use a voltage-controlled current source or a current-controlled current source. And here's two of the equivalent things right here. So this right here, this is a current source, but as you can see, it's being controlled by this voltage across right here. Okay, and here's the transconductance component right there. This is a current source, but it's controlled by the current going into the base right here. Okay. And remember what we had done. This is remember, this is called the hybrid pi model. And what the hybrid pi model is, let me back up a little bit, where we had, so here's like the original, right? So the original, you see, the pi resistance, R pi, right here. Then you have G mu and voltage CE right there, and that is controlled by that voltage. So, but you see, it is symmetric on both sides, okay? And then these right here, those were the Y parameters, okay? So it's the current right here coming in, for the input port, and then you have this current on the output right here, and it's a function of these voltages inside, the BEs and the CEs, those voltages, right here, okay, of this transistor inside. Now, the thing is that this term right here, the G mu, that was found to be very small. So we were able to get rid of this component right there, and then it became this, the hybrid pi model. Okay, so that's where that came from. This component is missing. Okay, so if we have this right here, oops. So if we have this right here, that's where this came from, and so we could model it with the voltage source or voltage-controlled current source. Okay, and you can even simplify it further if you want to ignore this input resistance right here. I mean the output resistance. So if you want to get rid of this right here, that's fine, and that's even more simplified. And that's if you're just looking at this for AC and DC. But if you want to look at what is the resistance seen looking in this way, you want to put that back because you'll need it at that point. Okay. So in that case, this current IC right here is just this beta times I, the input right here, so it's proportional to that. This right here, if that's really large, that's small, this component can be often neglected, and so it just equals that right there. Okay. Okay, so let's look at what is determined by, what it means to have a small signal. How small is small? Okay, so we'll define that by doing another sort of like Taylor expansion and then linearizing to find out what the limits are. So for small signal operation, changes in voltage and current should be linear. Okay, and that's for a small signal. So the small signal constraints on the BJT can be found by using the simplified transport model for the total collector current of the transistor in the active region. So that's where this came from, and I think that was like chapter 4 or chapter 5 of Digitron class. Okay, so let's take that as fact, what this is right here. So now we know that we can take this right here. This is the total current for the collector. We could break it up into components, the DC component and the AC component. Okay. And so for that, we have this right here, which is just, you're going to break this piece into two pieces, this piece and right here for that piece. So you'll identify this component right here as IC, and that's what you have right here. Okay. And then what you could do is you could take this and do a Maclaurin series, because you're going to expand that about this VBE being close to 0. And then you have all these terms right here. You have your 0th order term, your 1st order term, your 2nd, where that VBE is squared, your 3rd order term, where this right here is cubed, and so on. Okay. Now, what you can do is, if you were to factor this in right here, then what you could do is take this term and then this term right here and cancel them out, right? And so then all you have left is this piece right here. And that would equal this right here. Okay? So this next equation came from this right here. So you have this, and you subtracted this from both sides, this side and this side right here. Okay? Then you have this. And then these higher order terms right here, so the constraint on these higher order terms, if you want to neglect them, then basically you're going to assume that this first higher order term, out of all these higher order terms, this one right here is the largest. It just gets smaller and smaller because it's cubed to the fourth power, fifth power. Those terms get smaller and smaller. So this is the one that is your biggest limiting factor. You want this term right here to be much less than this term, right? This VB over VT, okay? So if this term right here is much, much less than this, then you can ignore it and everything else, okay? And of course, too, for linearity, you want this right here to be proportional to VBE, which is this one by itself, which means that IC over VT, this is the proportionality constant. So this is the equation, that's all you want. This piece and this piece right there. So you want something that looks like this. Okay. Oh yeah, I said over here, these higher order terms, the quadratic term, right here, the cubic term, and higher order powers, they correspond to harmonic distortion, which we talked about before in a previous, I think like chapter 10. That's harmonic distortion. Okay, so let's say you have this. So if you have this right here, where this first term of the higher order terms, if that's much, much less than your linear term right here, then that means that your VBE is much less than this, right? Do you guys see that? Let me just write out a little bit to show you. So let's say you have this, 1/2 VBE over VT, and that's squared, and you want that to be much, much less than your first linear term right here. So, so in this case, what you do is just solve for, this is squared, sorry. So you just solve for your VBE. So you have your VBE squared. We'll take that, put it on the denominator, and we'll take this, flip it, and put it on this other side, and we'll take this and put it on the numerator over here. So this is where we're getting that expression from. Okay, right here. So is what holds true, okay, for that condition. Now, this term right here, we've seen this before. This is the thermal voltage, right? And that's about 1/40, which is like 25 millivolts. That's what this is at room temperature. Okay, so keep that in mind. It's at room temperature. Okay. And so 2 times that is 50 millivolts right here. So what that means is that that implies that your VBE has to be less than this 50 millivolts. So yeah, let me explain this. Okay, so the thing is that when the book says much, much less than, what they really mean is like 10 times smaller than that. Okay? And maybe you need even smaller, maybe you need 100 times smaller. But in this book, that's what that means. So when you ever see much, much less, it means like an order of magnitude smaller. Okay, so that's why you have 0.05 here, but you have 0.005 right here. And it's no longer much, much less than. It's just that this just needs to be less than or equal to that, a magnitude smaller than that. Okay, so that's where the extra 0 came from. So here's the definition. For a small signal for BJT, the definition of that means that your voltage between the base and emitter right? It has to be less than or equal to 0.005 volts, or 5 millivolts. Okay, so that's what this is right here. So the voltage across here needs to be less than 5 millivolts for this thing to behave nonlinearly. That's a small amount of voltage, right? But the nice thing about that is even though the voltage across the input is very small, you have a huge amount of gain over here. And you can see that by the slope. It's a high slope, and you have a high amount of gain. So yeah, so what ends up happening right here is here's what the characteristic looks like. So that's the Q point right here, and this right here is this is like your DC going over. Your sinusoid is going up, higher, and lower by your VBE. And let's say this part right here, this line right here, is a 5 millivolt. Right, that's high as you can go. But what happens is that it goes up through here, it gets magnified, so your IC can oscillate at a much higher, and this is not even to scale, it's actually much, much higher than this. But there is the magnification of that, okay, as you can see here. Okay, and again, that's the hybrid pi model. Okay, so that defines at least the VBE voltage. Okay, so when someone says, you know, what does small signal mean? It means that the voltage VBE has to be less than or equal to 5 millivolts. Now, for IC, we could then extract what that needs to be, right? So for a 5 millivolt change in VBE, that corresponds to a 20% change in the collector current. Okay. And you just look at the ratio right here. So you have your IC over this IC right here. This IC is your transconductance times your VBE. We know what this is. This is going to be 5 millivolts. The ratio of this right here, the transconductance over the IC, that's your thermal voltage. Okay, that's going to be 25 millivolts. That's going to be 0.005. And that's how you're getting your 20%. Okay. So here's the whole thing for BJT. What small signal limit means for that, your VBE needs to be less than or greater than 5 millivolts, and your collector current, IC, needs to be less than or equal to 20% of IC. Okay. Any questions about that? Alrighty. Okay, so now let's look at the differences between N-type and P-type for these transistors. And I know this is like a review from like, I guess, Digitron. So I just want to remind you guys what this stuff looks like. Okay, so here's the bipolar junction transistor. Here's the metal oxide semiconductor field effect transistor. The differences between the two. NPN. I mean the PNP and NPN for both cases right here. And remember what P-type means. It means that the holes are the majority characters, and for N-type, the electrons are the majority characters. And here's what the circuit looks like for those cases, and the voltages and the currents and their directions, okay, for that and the MOSFET. Okay, so let's look at the small signal and compare these two together, and they're actually the same, even though you have different directions of the currents, okay? But I'll show you why they're the same. So, so small signal model for the PNP transistors is identical to that of the NPN transistor, even though the DC currents flow in opposite directions. Both transistors are biased by DC current IB, and that establishes the Q point, okay? So a signal current of IB is injected into the base of both NPN and PNP transistors. So here's the NPN, and you see here's the lowercase IB. Here's the signal that you're really concerned with. that's coming in this direction right here. And this is the total current, right? So you have I and capital B. But this I, capital B, has both of these. It has the DC component and the AC component added together, all coming into the base. Over here, this is the DC is going the opposite direction, but the signal, the IB, the small signal, is going into right here. So this current right here, the total, has components of both this one coming this direction and this one going this direction, all into the base. Okay? So that's this IB being injected into the base for both. So that's the same. So for the NPN transistor, the total base and collector currents are this right here. Okay, so here's the IB. Here's the IC right here. So here's the total. You have your signal, your AC, and your DC. Over here, you have your total. Look at the direction difference. And you have your IC going in and your capital IC, DC, going out. So in both cases, you have your ICs going in. Your small signals are going in, okay? But your DC's going in here, and your DC's going out there. Again, this is PNP, and this is NPN, okay? And this is the same thing for the total base and collector currents for the PNP. Okay, so for both the NPN and the PNP transistors, a signal current injected into the base causes a signal current to enter into the collector, and the polarities of the current control current source, the current control source and the small signal models are identical. Okay, so the difference between these two plots and these two plots is that on these plots right here, we're only looking at the small signal analysis. Okay? You don't see the total, you don't see the DC, you only see the small sinusoidal signal. And if you look at those are identical. And that's what the model is actually based on. Okay, it's not based on the DC, it's based on, even though the DC sets up your Q point, the analysis concerns the small signal. And those are identical for both the NPN and PNP. Okay. So anyways, that's the reason that they're identical. So, and again, this is the simplified version. Oh wait, it's not simplified because R0 is still there. Okay, but here's the hybrid pi model right here that both of these correspond to. Okay. All right, so let's look at next the common emitter amplifier. Okay, so for small signal characteristics, this is going to be for the common emitter amplifier, and it looks like this. And you can see some DC blockers here and here, and now we know more clearly what these do and why. And this right here is AC bypass. Okay. So to look at the common emitter amp, this is what we'll do. So first, we'll transform this into a more simplified version. Okay. So so this is going to be the AC equivalent. So we do the AC equivalent by doing this. We assume that all capacitors have zero impedance at signal frequency. Okay, so they block DC, so it's like infinite resistance, our reactance. But for AC, the AC is able to get through quite easily. Okay, so, and also, this is important too, the DC voltage source represents an AC ground. Okay, so that right here, this VCC equals 12 volts. This is the DC source. But now we're going to look at it as an AC ground in terms of AC. So think of it as a virtual AC ground. So if that's grounded up there, and that is shorted, and that's shorted, and that's shorted, then you're able to see how this over here becomes this, right? So you still have this input right here. You still have this resistor, right? But this piece right here is now shorted. So that's why you have this, right? And now you have this 104 kiloohms. So what this came from, here's a 160 kiloohm, and this right here is 300 kiloohms. But if you put these two in parallel, then you get a smaller resistance going to ground, right? Because remember, this is going to ground right here, but this is also ground in terms of AC. So going from here to here is also ground. Okay, so this point is identical to that point. So we can just fold it over and have it meet there. And that's what's happening here, but now they're in parallel because they're starting at the same voltage, the same high voltage, and ending at the same lower voltage. Okay, so that's where that comes from. This part right here is no longer there, right? And the reason why is because this is the AC bypass. So this DC blocker is also an AC bypass. So for AC signals, it looks like it just goes straight to ground from this point to here. Okay, so that's where that came from. And this right here, well, this part right here goes straight to ground. That's what this is doing. And this part right here is being short-circuited and going through here, this R3. And that's what it's doing over here. Okay. So does anyone not see what's going on here? Like any questions about that? Okay. All right, so the next thing to do is replace it with the small signal model, right? So here's what we left off with right here. And so we take this piece right here and replace it with our small signal model. So this is going to be the hybrid pi model right here. Okay, so it's hybrid pi because we don't have that voltage controlled current source right there. We took that off because it was negligible, right? So that's what's going on here. And then to go from here to here, what we do is just this part over here remains the same. Nothing's really changed over here. But over here, we combine all these together because they're all at the same voltage. They're all grounded right here, and they're all at high voltage right here. So all this right here is just called the R load. And they all have the same voltage across them. Okay. Now, the reason it's called common emitter, like common emitter, is because both the input and output, they all refer to a common ground. And that's this right here. Okay, so here's the input, here's the output, right? And both the voltages for the input and output, they're all referenced to this common ground right here. Now, of course, when you put this in your circuit, this may not be the ground of your circuit. It may not be zero volts, but with respect to the voltage right here across the input and output, it is common. Okay. So that's what really matters. So that's where that name comes from. Okay. Here's like a simplified picture of that, how they're sharing the common reference point in both cases. Okay. All right. Okay, so let's look at terminal voltage and also the resistance as well. Okay, so so let's get like an expression for the gain amplifier. Okay, so we're starting off with this right here, and then we ended up with this right here. And so you can see the voltage is the output voltage over the input voltage, right? Here's the output over the input. That's the gain of this whole thing, okay? But what you can do is you can look at this voltage right here, right? Because this is right before our simplified model of our hybrid pi model that's, in here. And you can say, well, to extract that out, I can place those in there and separate them out. Okay, so this VB right here, that VB, which is this voltage of your base, right? They cancel each other out and you get this back. But now we have it in terms of this ratio and this ratio. Okay, well, this ratio right here is called your ACE. This is that gain right there. Okay, and it's called your terminal gain. And it's the ratio between your output voltage and VB. So the ratio between this voltage right here, which is your output, and this right here, which is like your input to your transistor. So your terminal gain of your transistor. Okay. Yeah, that's the gain between the base and the collector terminals of the transistor. So what you can do with that, this voltage right here can be placed into something like this, where as seen by your transistor, this voltage is really like the source coming in. And you could do your KC, your voltage division, whatever, to find out what that is. But in terms of this right here, it looks like your V out right here is equal to negative conductance RL times your VB. Okay? So if you look at your V out right here, this V out, you have your RL times your current. In your current is your conductance times VB right here. That's what this is. And then, so what you do is, since you know that this is V out over VB, you just take this, plug it in here, and then the two VBs cancel out, and then you're left with this. Okay? And it says right here that the minus sign indicates that the common emitter stage is an inverting amplifier. Okay? So the input and output are 180 degrees out of phase. Okay? So that's what that's for, because it is an inverter. Now for the resistance, the input resistance, this part right here, as seen as looking in here, it sort of just looks like this resistance, right? If you sort of like encompass all this part right here and you're looking in. Okay? So what you can do is say, well, I can replace this right here with just this VB, which is that voltage right there, and some current, the equivalent current that's coming out of here. So you do have current going around this direction, right? And the current that's coming out of there is the same as the current that's going through this resistor, going through a voltage drop of VB, right? So that's what this is right here. This IB is this current. And so is this current going through that resistor is the same as the current coming out of all of here, right? So then you could just say your resistor IB is just your VB over IB, and that's the same thing as your R pi, that resistor there. Okay. So anyways, that's the input resistance. So any questions about input resistance or terminal voltage gain? Okay. All right. All right, that's it for today. A little early. So see you guys on Wednesday.